Hey everybody, welcome back. This is our final section of 12.2. Another example, we're gonna do a thought that we need for 12.4 later on. Let's just look at a two-dimensional vector, cosine of t and sine of t. Notice if I square each one, cosine squared and sine squared, they add up to 1. So this is a vector format for a circle and of radius 1. So if we do the time derivative, r prime of t, we get for the x component negative sine t, the y component cosine t. Let's take a look at it at a couple of values. I'm going to look at t equals pi over 4 and t equals 3 pi over 4. So if I plug in r pi over 4 into r, cosine of pi over 4 is the same as sine of pi over 4, root 2 over 2. When I plug it into the derivative, there we have sine and cosine the whole way. We just need to know whether it's negative or positive. So pi over 4 with negative sine t is going to be negative root 2 over 2. And then the y value in the derivative is cosine. It's root 2 over 2. If I do 3 pi over 4 in the second quadrant, x value is negative, y value is positive. When we take the derivative, we've got negative sine. Sine is positive in the second quadrant, but we're doing negative, so we got negative. And cosine is already negative in the second quadrant. So I plotted these. I drew the circle. I've got r evaluated at pi over 4, points there. R prime of pi over 4, remember it points in the same direction as t is increasing. What happens with r? So I got a vector pointing that way. And I do 3 pi over 4, I got negative and then up the same value. And if I do the derivative, it's left and down the same value because it's negative and negative. They look orthogonal, don't they? It's like right angles. Are they though? Is r prime of t dotted with r of t equal to 0? That's how we check for orthogonality. Let's take a look at it. So r prime of t is negative sine t cosine t. R of t is cosine t sine t. Let's dot them. I get negative sine t cosine t and cosine t sine t. Add them together, they do cancel out. We get 0. So for circles, the tangent lines or tangent vectors are orthogonal to the radius vector for all points on the circle. Notice in my dot product, I didn't specify a time. I used any t. So the radius is always orthogonal to the tangent vector on a unit circle. Not just a unit circle, any circle. Does this scale up to 3 dimensions? Yes, it does. In 2 or 3 space, if r prime of t exists, and the requirement of what we had in the last one, the magnitude of r of t has to be a constant. The radius cannot be changing length. If this is true for all t, that's the symbol for all, upside down capital A, then the dot product between the original vector and its derivative equals 0. And thus r of t is orthogonal to r prime of t for all t. Let's prove it. This is a fun proof. We use dot products here, so we're going to use dot products in our proof. But first we're going to make a couple assumptions. We do want r of t to be a differentiable vector function. We do want the magnitude of r of t to be a constant value for all t. Recall that a derivative of a constant is 0. So we will take the derivative of r of t dotted with r of t. R of t dot r of t, we take the derivative. Remember to do the product rule. We get r prime of t dotted with r of t plus r of t dotted with r prime of t. The left side, though, without the time derivative part, that's how we write the magnitude, r prime of t squared. So we have the time derivative on the left, time derivative of a constant value. The magnitude is constant. We declared that up here as the part of the requirements. These two are the same. We combine them together, we get 2. The left side equals 0. I can divide by 2 and I get RT dotted with R prime of T equals 0. This works in 3 space as well. So what is that in 3 space? What do we have when the radius is constant? We have a sphere of radius rho. This is going to be important in 12.4. This idea of this proof, it works for any vector and its derivative. The dot product works if the magnitude of the vector is constant. So we will be looking at this with the tangent vector dotted with its derivative in 12.4. That's for a later section. Peace.